Hi there, I'm Toby Swan at Toby Tutors Physics, and this video is going to be about energy transfers and conservation of energy. So what you need to know, what we're going to look at in this video is firstly, energy stores and transfers, the differences between those and how we can draw diagrams to represent them. The law of conservation of energy, one of the most important laws in physics. And finally, we'll look at some practice calculations, which often form a large part of your exams. So what is energy? It's a really hard thing to define. If you look in the dictionary, it will say energy is the ability to do work. But that in itself is a little bit confusing. I think the way to think about it is the ability to do anything. It's the ability to do stuff. Work we'll look at when we're talking about forces, but in itself is a tricky word. So just when anything happens, energy is required. It's probably the best way to think about it. It's measured in joules. It cannot be created or destroyed. It can only be transferred from one store to another. So that is the law of conservation of energy. As I say, absolutely fundamental, very common question. Just state the law of conservation of energy. It is the fact that energy cannot be created or destroyed. It can only be transferred from one store to another store. And so what are those stores? In Key Stage 3, I'm sure you'll have looked at these. You might have used different words. I'm just going to move that over a little bit. But so gravitational potential, kinetic, chemical, elastic potential, magnetic, thermal, electrostatic, and nuclear energy stores are the ones you need to know. Well, as I say, we'll talk about them in more detail in a second. But the way to remember them possibly, great kind chimps eat many tasty energy nuts. That's the best I've ever come up with, but if you can come up with a better one, let me know. But that's one way of remembering those 8 energy stores. You'll notice there I've also put in asterisks for some of these: gravitational, kinetic, elastic potential, and thermal. Those are all ones that you need to know and be able to describe mathematically as well. We're going to look at the first 3 of those today. Thermal we will cover in a atoms and particles video later on. But looking at these in more detail, gravitational potential energy is a store that is increased when you raise something up. There has to be a gravitational field. The Earth has a gravitational field on it. Anything with mass has a gravitational field, but generally we're talking about planets, and often we're talking about the Earth. So if I lift up this calculator, I am increasing its gravitational potential. Any of these ones where we have a potential in the name is really, you can't really visualize it, but it has potential to do other stuff, has a potential to transfer it into things that you possibly can visualize. So as I say, if you increase, or rather you increase the height of these objects, you will increase the gravitational potential energy. Kinetic energy is what you might have seen in Key Stage 3 or heard of in Key Stage 3 as movement energy. And so things that go faster have greater kinetic energy, and things that have more mass or are more massive have greater kinetic energy. If you want to get your remote control car working or your computer working, you might need a battery. Your car needs petrol. And all of these things contain chemical energy stores. So they, again, you can't see them, but they have the potential to do the stuff that an electric car would do, or do the stuff that food provides you, being able to move, being able to speak, being able to provide thermal energy, heat. Next one, elastic potential energy. Again, it's a potential energy, so you can't see it, but you can imagine it very clearly. If I stretch out a rubber band, then you know that if you let go of that rubber band, it's going to start moving. So if you've increased the elastic potential energy in that rubber band by stretching it out, and that is what elastic potential energy is. Magnetic, similar. You will know that if you have 2 magnets that are unlike poles, a north and a south, they're going to attract each other, so they have the potential to increase that kinetic energy as they come towards each other. Or if they're unlike poles, a north and a north, or a south and a south, they're going to push apart, and they potentially are going to increase the velocity and the kinetic energy. In these 2 examples, these magnets will attract each other, so they pull each other apart and they will start to move. Thermal energy store, again, fairly straightforward. Anything that has temperature has a thermal energy store. You will look at that in more detail when you're looking at particles and matter. But generally, for purposes of this video, we're talking about anything that is hot has thermal energy. Electrostatic, you might have done this in school. Everyone's favourite, getting the Van de Graaff generator out, and you can make your hair stand on end. But lightning is also an electrostatic store release. If you rub two insulators together, you get static charge. You might have given yourself an electric shock sometimes when you're walking on the carpet. Those are all electrostatic energy stores. And nuclear energy store, not one that you need to know massive details about as a store in itself, but within the nucleus of an atom, there are forces that provide these stores. When they're released, they can produce huge amounts of energy. You will look at that when you're talking about radioactivity, when we look at that topic as well. Okay, so as well as those stores, we said that energy can only be transferred from one store to another. It cannot be created or destroyed. And the way in which they change those stores is via these energy pathways. 4 of these that you need to know: mechanical, electrical, heating, and radiation. Mechanical happens whenever there is a force over a distance. So if you think about pushing something, okay, if you push an object, then you are increasing its kinetic energy store. How are you doing that? Well, there's going to be chemical energy inside your muscles. You're pushing and you're creating kinetic energy. But by pushing, you are creating a force and you're providing that force over a distance. So work has been done, and the type of work that's been done is mechanical. Electrical pathway or electrical transfer is whenever you have a current, an electrical current. So if you think about, we'll look at some examples in a second, but whenever you have a battery, that is a chemical store. You're providing heat energy from maybe a lamp or a heater. How is it getting from the battery to that heater? Well, it's going via electrical current. So the transfer or the pathway would be current, electrical current. Heating is whenever something has a temperature gradient. So I've got a nice cup of coffee here. I've got a nice cup of coffee here. I've got freezing hands, but I put my hands around this coffee, and the warmth, the thermal energy from the coffee is literally transferring from the coffee into my hands. And that is a heating transfer. Finally, radiation. That is one form of heating transfer as well, but it's also whenever any energy radiates. So any form of wave, basically, whether it's sound waves, the fact that I'm speaking to you, the sound is coming from the speakers on your computer or your phone to your ears. How is that energy getting from one place to another? It's by radiation via waves. The way to remember these 4, many elephants hate running. Again, if you've got a better one than that, let me know, because I'm always open to a better one than that. Okay, so let's look at an example of how this would work and what you'd be expected to do in an exam. I've got an example here I talked about earlier, an electric car, remote control car, and within this car, you've got a battery. Okay, that battery contains a chemical store. Within that battery, there are chemicals that potentially can release energy into different forms. So when you turn the car on, ultimately what that car wants to do, what you're trying to get out of that car, is most likely kinetic. You want that car to move. Okay, there might be flashing lights and things as well, but let's keep it simple. We want it to transfer into a kinetic energy store. So we can create these energy diagrams, and we have a store here and a store here, a store at the beginning and a store at the end. And then we want to talk about how the energy transfers from one to the other. We can't just say it just disappears, this chemical store disappears. It transfers into that kinetic energy store. And to do that, it needs to use one of those transfers, one of those 4 transfers that we talked about. In this case, whenever there is an electrical current, we can say there is an electrical transfer. So as I said, energy cannot be created or destroyed. The energy must be coming from another store. That is the conservation of energy that you will so often need to state as a definition in your exams. In this case, the chemical energy store of the battery is decreasing, and the kinetic energy of the car is increasing, and so the chemical energy from the battery is being transferred via an electrical current transfer to the kinetic energy of the car. So have a look at how that diagram is constructed, and here are some example questions for you to have a go at. See if you can draw the energy diagrams and explain what is happening in terms of energy transfers in these 4 situations. I'll give you the answers in a second. Okay, so the answers. The hand's been warmed up. I gave that exact answer, that exact example a second ago. So you've got a thermal store in the cocoa or the coffee. You've got a thermal store in your hands. Your hand's been warmed up. What is the transfer? It is via heating. A car slowing down by applying brakes, a slightly harder one. Well, it starts off with a kinetic energy and it ends up without kinetic energy. But where does that energy go? It cannot be created or destroyed. Importantly, it cannot be destroyed. So it must have gone somewhere. And in the case of anything stopping, it's going to be producing possibly a little bit of sound, but mostly thermal energy. And how does it happen? Well, there must be a force from the brakes or a force from the friction of the road stopping that car, slowing down that car, reducing the kinetic energy. And so the transfer is going to be mechanical. You've got the force and you've got the distance. So it's a mechanical transfer. Ball speeding up as it falls from your hands. So in this case, you start off with quite a large potential energy. It's high up. You drop it and it speeds up. It turns into kinetic energy. What's the process? What is the transfer? Well, again, there is a force. Not so obvious because no one's pushing it, but something is pushing it or something is pulling it. Gravitational force is pulling it. Okay, the weight of that ball is pulling it downwards towards the earth, and it's pulling it down with a force over a distance. If there is a force and a distance, then it is a mechanical transfer. Finally, a guitar chord causing your eardrum to vibrate. Very similar to the example I gave earlier. You've got kinetic energy of the guitar string or strings vibrating. Then it's getting to the kinetic energy of your eardrum vibrating. That's how your brain recognizes that as a sound. How does it get from one to the other? Well, another topic we'll look at is waves, and anything that is waves transferring energy is a form of radiation. So those are your 4 answers. Okay, as I said, these 4 types of energy store, you need to know the mathematical details of, be able to use the formulae. We're not going to look at this last one, thermal energy. We'll save that for another video. But kinetic, gravitational, and elastic potential we're going to look at now. And it's really just practicing applying the formulae that I'm sure you're aware of. But let's have a look at them. So kinetic energy, the formula is, hopefully you're saying it in your heads right now, but the formula is half mv squared. Kinetic energy is half times the mass times the velocity squared. Importantly, I will always stress this, the units you need to be aware of. You need to make sure that your kinetic energy is in joules, that your mass is in kilograms, and that your velocity is in meters per second. You also need to make sure that if they're not in those units, you transfer them. You change them into the units here. So if they're prefixed, as we talked about in the first video, you need to transfer these into joules, kilograms, and meters per second. Okay, so there is the formula in symbol form. Kinetic energy is half mv squared. Make sure you've got those units correct. And some people like these little triangles. I'm not a big fan myself, but if that's what you like, then go for it. So in this case, you've got these two multiplied together and these divided. Okay, so how can we apply it? Well, I'll do a little example here. Kinetic energy of a tennis ball of mass 59 grams served at 30 meters per second. Best way to approach these is to write down the information. You're calculating, so obviously it's going to be using a formula. You've got a mass and you've got a velocity. So let's write down the information we've got. M, or mass, is 59 grams, but hopefully alarm bells are ringing and you're realizing that that is not in kilograms. It needs to be in kilograms, so we're going to say 0.059 kilograms. My velocity is 30 meters per second. I'm still going to check, are those units correct? Meters per second is the standard unit for velocity, so yeah, I'm happy with that. And I want to find out my kinetic energy. My kinetic energy, I do not know. But now I've got this information, I know we've just looked at this topic, so it's obvious what the formula is, but it might not be so obvious in the exam. But hopefully now you've got this information down, you can look through your formula sheet and see which formula is it that I need that contains those three things. And I can use this formula. Kinetic energy is half mv squared. I can just substitute this in, okay? I need to substitute. You can rearrange. In this case, you don't need to rearrange, but in future questions, you might need to rearrange. But your best bet is always to substitute first to maximize those marks. So kinetic energy is half times the mass in kilograms, 0.059, times the velocity squared. Make sure you're being careful with your calculator. Make sure you're using any brackets so that it doesn't square the wrong thing. And your final answer comes to 26.55 joules. Another example here, calculate the mass of an athlete running with a kinetic energy of 1,600 joules at 8 meters per second. Again, we're going to write down the information. So what do we know? We know that the kinetic energy is 1,600 joules. Check the units, it's in joules, and that's what I need it to be in. Velocity, 8 meters per second. Check units, it's in meters per second, that's what I want. So we're all good with units, we don't need to change anything, but we do want to determine the mass. Again, kinetic energy is half mv squared. Let's substitute. Rather than rearranging, let's substitute. Unless you're really confident with rearranging, just substitute those things in. So we've got 1,600 equals half times m times 8 squared. And I can complete those numbers. Let's do 1,600 equals 64 is 8 squared times a half, 32 m. So m equals 1,600 divided by 32, which comes to 50 kilograms. Also do a mental check. Now I know something about masses. 50 kilograms for an athlete, probably a child. It's not a very heavy athlete, but that is not a ridiculous weight. We're not talking about tons, we're not talking about grams, we're talking about the sort of mass that a person, an athlete, would have. Finally, final example here, calculate the velocity of an F1 car with a mass of 600 kilograms and a kinetic energy of 1.08 megajoules. So again, let's get this information down. What do we know? We know that the mass is 600 kilograms. Are the units correct? Kilograms are the units we want for mass, so that's all good. Kinetic energy, 1.08 megajoules. Hopefully you're screaming at me. Not megajoules, we want it in joules. So that equals, remember the multiplier is times 10 to the 6. So 1.08 times 10 to the 6 joules. You could either just type that into your calculator, or you could do literally 1.08 and then multiply it by 10 to the 6. What do we want? We want the velocity. So again, it's obvious in this case what the formula is, but we've determined now that this is the formula we're going to use. Kinetic energy is half mv squared. Rather than rearrange it, I would suggest again that you substitute the information in. So 1.08 times 10 to the power of 6 equals half times the mass, which is 600, times v squared. Now, I can simplify this a little bit. 1.08 times 10 to the 6 equals 300 multiplied by v squared. So 1.08 times 10 to the 6 divided by 300 equals v squared. Then I get 3,600 equals v squared. So how do I get v on its own? I need to square root both sides. So square root of 3,600 is v, which equals, square root that quickly, 60. A very nice round number, which is always a good sign. What have I worked out? I've worked out the velocity. So don't forget my units here. Meters per second. And a mental check, does that make sense? An F1 car going at 60 meters per second means that in 1 second it's going to have travelled 60 meters. Now that's pretty fast, but again we're talking about an F1 car. That's not an unreasonable speed or velocity. Okay, over to you for some you-dos. Let's have a go at these questions. I'll give you a second. Oops, giving you that answer. Have a go at those questions. Pause the video and I'll be back in a second. Okay, and using the same ideas as I just have, hopefully these are the answers you've got. Written them in joules and in kilojoules. Okay, so the next type of energy we're going to look at is gravitational potential energy. Remember, it's gained when you lift something up, or it's lost when something falls. And the formula that you need to be aware of is that gravitational potential energy is mass times the gravitational field strength times the height or the change in height. Mass, got to be in kilograms. Gravitational field strength is how strong that field is on a particular planet or in a particular place, and it's measured in newtons per kilogram. And the change in height or the height is going to be in meters, and gravitational potential energy is in joules, of course, because it's energy. On Earth, which is where we do most of our questions, the value for gravitational field strength is 9.8. But whatever your exam says, often it will say in the question, use that value. If it doesn't state it, then use 9.8. But do read the question carefully, as always, and use whatever value it says. So that's what it would look like as a symbol formula, and there's your triangle. Okay, we're going to look at one example here, and then I'll hand over to you. A 10,000 kilogram aeroplane takes off and ascends to a height of 1.5 kilometer. How much gravitational potential energy has been transferred to the plane? So in this case, let's again write down the information we have. We have that the mass is 10,000 kilograms. We have that a height is 1.5 kilometers or kilometers. And we have that our G, because they've told us in the question, is 9.8 newtons per kilogram. Hopefully you've noticed that I have forgotten something there. I have not changed my height into meters. So I need to change that into meters, which is 1,500 meters. Now, hopefully very straightforward. Gravitational potential energy is mg. Sometimes you'll see it as h, sometimes you'll see it as delta h, which just means a change in the height. Okay, it's ascended, so that is a change in height. Now I can substitute very straightforwardly. 10,000 multiplied by 9.81 multiplied by 1,500. Put it into your calculator, and you should have 147,000,000 joules. Quite often, a number like that, they're not going to say write it like that. They're going to say write it in megajoules. So you're going to need to change that into a prefix value. In megajoules would be 147 megajoules. So megajoule is a million joules. So you're going to divide that by a million. Okay, have a go at the next two questions. And your answers. Of course, you could have had this answer in meters, 3.06 meters for question 2, but I've converted it there into centimeters. Okay, the final one we're going to look at, the final energy store we're going to look at today is elastic potential energy. Again, the formula you need to know. It's the amount of elastic potential energy an object has is found using this. Elastic potential energy is half times the spring constant times extension squared. You'll have looked at what the spring constant is. Again, this is a forces topic, but I thought it was worth putting in this energy video for now. But if you're not sure what the spring constant is, I'll be doing a forces video very soon. Units for energy, of course, it's energy, so it's going to be in joules. Spring constant is newtons per meter, and extension is meters. So extension squared would be meters squared. And there's the formula in symbols and your triangle. So let's apply it. Straightforward one, and then two questions for you. A spring with a spring constant of 11 newtons per meter is stretched 20 centimeters. How much elastic potential energy is stored? So as always, hopefully you know the drill now. We're going to write down the information we have. We know that the spring constant is 11 newtons per meter. So K is our spring constant, is 11 newtons per meter. We know that the extension was E, and that is 20 centimeters. We want to know the elastic potential energy. Need to have checked that extension. Since centimeters, I need it in meters. So elastic potential energy is half times K times E squared. In this case, we've got all the information we need. Half times 11 times 0.2 squared, and our final answer should come to 0.44 joules. Okay, over to you for a couple more examples. And now the answers. Okay, again, that's been put into centimeters. You could have had it in meters, 0.18 meters. Okay, so in this video, we've looked at the 8 energy stores and how to remember the names of them, stated the 4 energy transfers and how to remember the names of them, explain how energies are transferred to different stores using an energy diagram. We've talked about and explained the law of conservation of energy quite a few times, and we've used kinetic energy, gravitational potential energy, and elastic potential energy formulae. Hope you found that useful. Look forward to seeing you soon. So if you found the video useful, don't forget to check out other videos on this platform, or go to my Facebook page here, where I've got other free resources, or feel free to book a call at tobytutorsphysics.com as well. See you soon. Bye.